Right now, this very second, there are countless other versions of you. Yeah, I'm serious. There's one where you took that other job, another where you said yes instead of no, one for every single choice, big or small, you've ever made. Now, I know what you're thinking. That sounds like something straight out of science fiction. But what if I told you it's actually rooted in one of the most serious, most debated ideas in all of modern physics?
This absolutely wild idea is a real scientific theory. It's called the many-worlds interpretation of quantum mechanics, and it suggests that our universe, well, it's just one tiny branch on an infinitely branching tree of realities. So over the next few minutes, let's dive in. We're going to unpack what that really means, why anyone would even propose something so strange, and whether it's even possible to test it. Okay, so to really get our heads around many worlds, we have to start with the deep, deep puzzle it was created to solve. A problem that sits right at the heart of quantum mechanics, and it's called the measurement problem. For almost 100 years now, quantum mechanics has kind of had this split personality. See, on the one hand, you've got this beautiful, elegant rule called process 2. It says that as long as we're not looking, a quantum system, like an electron, just exists in this ghostly blend of all its possible states at once. It's called a superposition. But the moment we try to measure it, bam! A totally different rule, process 1, violently takes over. That smooth, predictable wave of possibilities just instantly and randomly collapses into one single definite outcome. It's like the universe has two completely different sets of laws, one for when it's being watched and one for when it's not.
And that's the billion-dollar question, right? Why? Why does the simple act of looking at something fundamentally change the laws of physics? And what even counts as an observer anyway? Is it a person? A camera? What about a cat? This question absolutely tormented physicists like Einstein and Schrödinger for decades, and it's what paved the way for a truly radical new idea. So picture this, it's the 1950s, and a brilliant grad student at Princeton named Hugh Everett III is looking at this whole mess. And he asks this breathtakingly simple, almost childlike question. What if we just get rid of the messy collapse rule? What if there's only one rule, not two? And this was his big idea. He basically said, let's take that one elegant rule, the Schrödinger equation that describes the smooth wave of possibilities, and just assume it's the whole story. That's it. It applies to everything, all the time. Particles, people, planets, you name it. No special exceptions for measurement. The collapse, Everett argued, is an illusion. It never actually happens. And this is where it gets really mind-bending. Here's the consequence. So before you measure, say, an electron spin, it's in a superposition of both spin up and spin down. Now, when you go to measure it, you don't force it to pick one. No, instead, you become part of the system. You get entangled with it. And at that exact moment, reality itself splits in two. The entire universe branches. In one universe, a version of you sees spin up, and in another, totally separate universe, an identical version of you sees spin down. Both outcomes happen. Both are completely real.
So what does this actually mean for us, practically speaking? Well, it means that we are always living inside a gigantic, constantly branching quantum state. Everett came up with this term, the relative state. Think of it like this. The outcome you observe is only real relative to your specific branch of the universe. From your point of view, the you who's now in the spin-up world, it looks for all the world like the wave function collapsed. The chance of seeing spin down just dropped to 0. For you. So it perfectly explains our experience without having to invent some weird magical collapse rule out of thin air. But this brings us to the biggest, most common objection to many worlds. It's a real head-scratcher. If every possible outcome is guaranteed to happen on some branch, what in the world does probability even mean? How can we say something has a 50-50 chance if both outcomes are 100% certain to happen somewhere? To get a handle on this, let's try a little thought experiment. Imagine you sign up for a study. They give you a sleeping pill, and while you're out cold, a quantum measurement is performed. If the result is up, they carry you to room A. If it's down, they carry you to room B. Okay, so you wake up, you know you're in a room, but your eyes are still closed. Now, you also know that the universe has branched. There's a version of you in room A, and there's another version of you in room B. But the you who is currently thinking and asking the question has no idea which one you are. So you can still meaningfully ask, what are the odds that I'm the one in room A? It's this idea of post-measurement uncertainty that lets someone inside a branch talk about probabilities, even though from a God's eye view, everything has already happened.
And what's really incredible is that physicists have worked out that if you're a rational agent in this situation, the only logical way to bet on which room you're in is by using a rule that's been a cornerstone of quantum mechanics for decades, the Born rule. It basically says that not all branches are created equal. Some are, in a sense, thicker or have more weight than others. So the very idea of probability that seems to be a problem for many worlds actually emerges naturally from its own structure.
Okay, I hear you. This is all very philosophical, very cool to think about, but let's get real. The biggest criticism you'll hear is that since we can't pop over and visit these other worlds, the many worlds interpretation isn't testable. And if you can't test it, it's not really science, right? It's just metaphysics.
But here's the thing. The physicists who actually work on this stuff argue that's just flat out wrong. Many worlds and the standard collapse idea might seem like they give the same results in our everyday lives, but fundamentally, they make different predictions about how reality works. And that means, at least in principle, you could design an experiment to see which one is correct. So how on earth would you test it? Well, you'd have to perform what's called a super experiment. The goal would be to put a really big object, something large enough to count as an observer, into a superposition, let the universe branch around it, and then try to reverse the whole process. If you could undo the measurement and see the branches interfere with each other, it would prove the other branches were real all along and no collapse ever happened. Now, to be clear, this is way beyond our technology today, but it's not thought to be physically impossible. And this brings us to a really fascinating twist in the argument. Proponents of many worlds flip the script. They say the burden of proof isn't on them. In science, we have this idea called Occam's razor. The simplest explanation is usually the best. Well, many worlds advocates say they're not adding anything to quantum mechanics. They're taking something away. They're just taking our single best, most tested equation, the Schrödinger equation, and saying, this is it. It's the people who believe in the collapse who are adding a whole new, mysterious, unproven piece of physics to the puzzle. So what's the big takeaway here? Maybe it's this. For centuries, we thought we were at the center of the universe. Then Copernicus came along and showed us we're on a little rock orbiting an average star. Then Darwin showed us we're just one branch on the vast tree of life. Could many worlds be the next great humbling? The theory that tells us that our entire reality, our whole story, isn't the one true timeline, but just one of countless, equally real pages in the grand cosmic book.